Right then, listeners. Ever get that feeling? That some problems are just, well, impossible.
I know what you mean.
Like, imagine trying to untangle a whole year's worth of Christmas lights.
Oh, the horror.
Or picture this, predicting the stock market with, like, absolute certainty.
Now, those are some seriously tangled knots.
What if I told you there's this whole field emerging, bubbling away, that aims to tackle exactly those sorts of puzzles, ones that seem impossible? It even goes beyond that, into areas like finance, logistics.
Cracking current encryption, even.
Absolutely.
Yeah.
Even revolutionizing medicine. It's a big one. It's called quantum computing.
Quantum computing. It does sound a bit intimidating, doesn't it?
Now, before you switch off thinking this is just for the super geniuses, the folks with a shelf full of physics PhDs.
Hang on a minute.
This deep dive is specifically for you. I mean it, whether you're a tech enthusiast or just have a little bit of curiosity about what the future holds.
We're here to demystify it all.
We're going to break down those core ideas, those big concepts, and we're going to show you that getting started in this mind-boggling world of quantum.
It's actually more straightforward than you think.
Much more. So buckle up, get comfy, and let's get started. Your quantum journey
Begins
right now. Today, we're diving headfirst into quantum computing for beginners, how to get started.
That's right. Our mission today is to unravel what this exciting field is all about, why it's causing such a stir in the tech world, and most importantly, to show you how absolutely anyone can start exploring it.
Exactly. We don't expect you to be, quantum physics whizzes already.
No, not at all. You don't need to know your Schrodinger's cat from your Cheshire cat.
Not at all. Our promise to you is to keep this conversation jargon-free, in plain English.
Simple.
No going down technical rabbit holes, no getting lost in the weeds.
Our goal is to equip you with a crystal clear understanding of where to begin your quantum adventure.
Exactly. Think of us as your guides on this journey, a journey into a technology that honestly has the potential to reshape our future.
Absolutely. So, let's jump right in. Let's start with what makes quantum computers so utterly different from the laptops or smartphones we're using every day.
It all boils down to, the basic unit of information.
The building block, if you will.
Okay, let's unpack that a bit. In your everyday computer, right, everything runs on bits.
The ones and zeros.
Ones and zeros.
Yeah.
A bit is like a light switch. It can be either on, which is 1.
Or off, which is 0.
Exactly. This binary system, it's the bedrock of everything in classical computing.
The foundation.
Now, quantum computing throws a curveball into the mix. It introduces this rather bizarre concept called a qubit.
A qubit.
Now, here's where it gets a bit mind-bendy. A qubit isn't limited to being just a 0 or a 1.
It's not so simple.
It's got this almost magical ability to be in a combination of both states at the same time. Simultaneously. And that, my friends, is what we call superposition.
Superposition.
Superposition. It sounds a bit like what my toddler says about his toys. It's a car and a spaceship at the same time.
Well, in a way, it's not a bad analogy, at least at a very basic level.
So it is kind of like that?
Let's think about a coin. A regular coin spinning in the air. Until it lands, it's not heads or tails, right? Well, it's kind of both. Exactly. It's in this fuzzy state that embodies both possibilities. A qubit in superposition, it's similar. It exists in this kind of blurry state of both 0 and 1, until we measure it, that is. Then it collapses into one of the two.
So until we peak, it's in this, quantum limbo.
Precisely. Now, if we want to get a bit more technical, and I promise to keep it light, mathematically, we represent the state of a qubit, let's call it ACE, that's the Greek letter psi, as a combination of the 0 state and the 1 state. We write that as S etois plus 1 psi. Now, M and psi, those are what we call probability amplitudes. In simple terms, they tell us the likelihood of finding the qubit in either the 0 or 1 state when we measure it. And here is a crucial point. The squares of those amplitudes, A2 plus VO, they always add up to 1. This reflects the certainty that when we measure the qubit, it's got to be in one of those states.
It's like the universe is saying, pick a lane, qubit.
In a way, yes. But this whole business of a qubit being in both 0 and 1 at the same time, the superposition, it's the very bedrock of what gives quantum computers their edge.
Their advantage.
A classical computer would have to plod through each possibility one by one, like checking every key on a giant key ring. But a quantum computer
is checking all the keys at once.
Precisely. It can explore a vast number of possibilities simultaneously, and that leads to a potential for exponential speedups for certain problems.
So it's not just a little bit faster, it's like warp speed compared to our regular computers.
For specific tasks, yes, it has that potential. Because those qubits, they're not limited to one state at a time. A quantum computer with, say, even a handful of qubits can explore an enormous number of possibilities all at once, in parallel. And that parallelism is what gives it the potential for those huge speedups for specific types of calculations.
Okay, so we've got superposition, this both at once state. Are there any other quantum quirks we need to wrap our heads around?
Oh, there's another one. And it's a big one. It's called entanglement.
Entanglement, that sounds a bit complicated.
It is a bit mind-bending, I'll admit,
Okay.
but also incredibly cool. So when two or more qubits get entangled,
They get, what, tangled up together?
well, sort of, their destinies become intertwined, they're linked, no matter how far apart they are. It's like they have this secret, unbreakable connection.
I remember reading about this. Wasn't it Einstein who called it spooky action at a distance?
That's the one. He wasn't entirely fond of the idea, but it's a real phenomenon. If you measure the state of one entangled qubit, boom, you instantly know the state of the other, even if they're miles apart, light years even.
No way. So even if those qubits were on opposite sides of the universe,
The connection would still hold.
it's
Yeah.
insane. Is there like a simpler way to picture this entanglement thing?
Let's imagine we have two boxes. In one box, there's a left-handed glove. In the other, a right-handed glove.
Okay, following.
Now, you open one box and see a left-handed glove. Bam! You immediately know the other box has the right-handed glove. You don't even need to open it.
Ah, I see. They're a pair.
Exactly. Now, entangled qubits, their connection is far more profound and useful than our gloves, but the principle is similar. They're linked instantly.
So those entangled qubits, they're like a superpowered team working together in this mind-boggling way.
Absolutely. And this interconnectedness, this entanglement, it's a powerful tool. It's something that quantum algorithms can leverage to perform incredibly complex computations. The combination of those two big ideas, the ability to be in multiple states at once, that's superposition, and this interconnectedness between qubits, that's entanglement. That's what gives quantum computers the ability to crunch numbers in a way that classical computers just can't compete with. It's all about parallel processing on a scale we've never seen before.
Okay, got it. Superposition and entanglement. Two sides of the quantum coin.
Now, you also mentioned something called the Bloch sphere earlier.
Ah, yes, the Bloch sphere. Sounds a bit like something out of Star Trek, doesn't it?
It does have a certain ring to it, doesn't it? Essentially, it's a visual tool. It helps us picture the state of a single qubit.
So how does it work?
Imagine a sphere, like a globe. The north and south poles, they represent our classical states, 0 and 1.
Okay, I'm picturing it.
Now, any point on the surface of that sphere, anywhere at all, that represents a possible superposition state for our qubit. It's a way of visualizing the fact that a qubit isn't just on or off, 0 or 1, but can exist in this whole spectrum of possibilities. And those values, how they're represented on the Bloch sphere, they are important because they allow qubits to exhibit wave-like behavior, leading to things like interference, which are really important in quantum algorithms.
So the Bloch sphere is kind of like a map of a qubit's potential.
A good way to think about it, it's a tool that helps researchers design and understand quantum operations. But for someone just starting out, understanding superposition, that's the key takeaway.
Right, qubit superpowers. Superposition, entanglement, and this Bloch sphere map. All very cool. But for us non-physicists, why should we even care about all of this quantum stuff? I mean, how does it actually impact our lives?
That's the big question, isn't it? And it's an important one. The unique properties of these qubits, superposition and entanglement, they give rise to the potential of this technology to transform so many aspects of our world. Quantum computers, with their ability to process mountains of information simultaneously, it opens doors to solving problems that are just completely out of reach for even the most powerful supercomputers we have today.
So we're talking about problems that are basically impossible for our current computers to solve.
In a practical time frame, yes.
Okay, I'm intrigued. But give us some examples, real-world stuff. Where could this quantum leap actually make a tangible difference? Something we can relate to.
All right, how about this? Cryptography. It's how we keep our online information safe. Shor's algorithm, which is a quantum algorithm, in theory, it can break a lot of the encryption methods we use today to protect our online communications, our banking, everything.
Wait, so quantum computers could be used to hack into our most secure systems?
That's a possibility we need to prepare for. To give you an idea of the scale of this, Classical computers, they'd take an absurdly long time to factor the huge numbers that form the basis of a lot of modern encryption.
Like longer than the universe has existed.
Potentially, yes.
Ah,
But
yeah.
Shor's algorithm, running on a powerful enough quantum computer, it could theoretically do it in a practical time frame.
Okay, so there's the scary side. But you're also saying that quantum computers could lead to the development of even stronger, more unbreakable encryption methods.
Precisely. It's a two-way street. We need to stay ahead of the curve. The development of what we call post-quantum cryptography, encryption that can withstand quantum attacks, that's a hot area of research right now, and it's crucial.
Right, so it's a cybersecurity arms race. What other areas could quantum computing shake up?
Optimization problems, these are everywhere. Imagine being able to find the absolute best delivery routes for, say, a massive fleet of delivery trucks, or optimizing incredibly complex financial portfolios. Quantum computers could revolutionize logistics, finance, even manufacturing, saving time and resources on a scale we can barely imagine.
So massive efficiency gains across a whole range of industries.
Absolutely. And then there's AI, artificial intelligence, everyone's talking about it. Well, quantum-enhanced machine learning, that could analyze huge data sets far more efficiently than we can today, leading to breakthroughs in pattern recognition, predictive analytics.
Hold on, so we're talking about, like, predicting the weather with pinpoint accuracy, or personalized medicine based on an individual's genetic makeup.
Those are definitely possibilities. And of course, there's material science and drug discovery, hugely important fields.
Yeah, the potential to discover new life-saving drugs, new materials.
Exactly. What's especially exciting here is the potential to simulate quantum systems, things like molecules and materials, simulating them at a level of detail that's just impossible for classical computers.
Why is that?
Because of the sheer complexity. Classical computers just can't handle it. But quantum computers, they could help us design brand new materials with very specific properties.
So we're talking about, like, designing new drugs that are far more effective, or materials that are lighter, stronger.
Or even superconductors that work at room temperature. Think about the implications for energy transmission. It's mind-blowing.
Okay, you've sold me. Quantum computing is important. It's potentially world-changing. But how on earth does someone like me with, let's be honest, zero background in quantum physics, how do I even begin to learn about this stuff?
That's the million-dollar question. And the good news is there's more and more resources out there that are specifically designed for beginners.
That's a relief.
The key is to start with the fundamentals. Build a strong base. Just like building a house, you need a solid foundation.
Got it. So where do we start digging? Are there any resources you particularly recommend for someone who's completely new to this?
Absolutely. One great starting point is a resource called Quantum Computing for the Very Curious. It's designed to be very interactive, using simple language and engaging examples to break down those core quantum concepts we've been talking about.
Interactive learning, that sounds much more fun than, slogging through a textbook. What else is out there?
If you're looking for a more structured, in-depth approach, I'd recommend checking out the edX Quantum course offered by MIT. It's a free online course that covers a lot of ground. It does assume you have some basic high school math and physics, but it's fantastic for getting a really solid understanding of the field.
MIT. Well, that's a pretty impressive endorsement. What if someone's more of a hands-on learner, someone who wants to jump right into the practical stuff?
For that, the Qiskit textbook is brilliant. It's another free online resource, and it's comprehensive. It takes you from the absolute basics all the way to advanced topics. And crucially, it includes loads of tutorials, coding exercises, and real-world examples.
Ah, so you can put what you're learning into practice straight away.
Exactly. And the Qiskit textbook is closely linked with Qiskit, which is IBM's open-source framework for quantum programming.
Hold on, quantum gates. What are those?
Think of them as the basic operations you can do on qubits, sort of like logic gates in a classical computer, but they can actually manipulate the superposition and entanglement of the qubits. The Qiskit textbook will walk you through using them to build quantum circuits.
So you can learn the theory and then immediately try it out with Qiskit. That's a pretty cool way to solidify your understanding. What about coding specifically? Any resources for that?
If you're keen to dive straight into coding, definitely check out the Microsoft Quantum Katas. These are interactive exercises that use Q#, which is Microsoft's quantum programming language. They're designed for beginners and offer a really hands-on way to learn by actually writing code.
Fantastic. So we've got interactive introductions, a structured university course, a comprehensive textbook with coding examples and coding challenges. There's something for everyone.
Exactly. There are so many options out there, it can feel overwhelming.
It does make your head spin a bit. Do you have any tips on how to actually create a study plan, especially for those first few weeks when you're just starting out?
Absolutely. It's important to have a plan.
Lay it on us. Give us a roadmap.
All right, so in those first 2 weeks, I'd recommend focusing on getting comfortable with the most fundamental concepts. Things like the difference between a bit and a qubit, superposition, and entanglement. Use resources like quantum computing for the very curious, and really focus on building that intuitive understanding. Don't worry about getting bogged down in the maths at this stage.
So the initial phase is all about building a solid conceptual foundation.
Exactly. Then, as you move into weeks 3 and 4, you can start digging a bit deeper. Maybe enroll in that MIT EDX course and start working through those early modules on the fundamental quantum algorithms. Alongside that, begin exploring the Qiskit textbook, working through the early chapters that introduce you to quantum gates and how they work on qubits.
So starting to bridge the gap between the high-level ideas and the more, well, formal representations.
Right. Then around weeks 5 and 6, take the plunge and create that free account on the IBM Quantum Experience. Try running some basic quantum circuits, the ones that demonstrate superposition and measurement. And to complement that, work through some of those Microsoft quantum katas to get a taste of coding in QShark.
So actually getting your hands on some, well, virtual qubits and starting to write some basic quantum programs.
Exactly. Then, from week 7 onwards, it's all about building on that foundation. Start exploring more advanced topics as you feel ready, like quantum error correction. That's a crucial part of making quantum computers work reliably. And maybe start looking at more complex quantum algorithms.
So slowly but surely, we're moving up the quantum ladder.
The key is to be consistent. And remember, join online forums, connect with other learners. Learning together, sharing your struggles and successes, that's a huge motivator.
It's like having a support group for your quantum journey. Now, it's probably worth acknowledging that not everything is smooth sailing, right? Beginners often hit some bumps in the road.
Oh, absolutely. Quantum computing has a bit of a reputation for being, well, challenging.
So what are some of the common roadblocks that beginners often encounter? And more importantly, how can they overcome them?
One of the biggest hurdles is the maths. Quantum computing relies heavily on concepts from linear algebra, complex numbers, and probability. It can be a bit intimidating, especially if you haven't encountered these topics before. The key here is to start slow. Focus on understanding the basic applications of those mathematical concepts, specifically how they relate to quantum computing.
So don't try to swallow the whole mathematical elephant in one go.
Exactly. Take bite-sized pieces. Use visual aids like the block sphere to build your intuition, and take advantage of those online resources that explain things step by step. There are also lots of exercises out there that can help you gradually build up your mathematical confidence.
Got it. What about the jargon? It seems like there's a whole new vocabulary to learn. Superposition, entanglement, decoherence, quantum gate.
Ah, yes, the quantum lexicon. My advice, build your own quantum dictionary. Every time you come across a new term, write it down, define it in your own words, and try to use it in your own explanations. Also, don't be shy about asking for clarification in forums or study groups. There are plenty of people out there who are happy to help.
So actively engage with the language, build your personal glossary, and don't be afraid to ask dumb questions.
There are no dumb questions when you're learning something new.
What about motivation? How do you stay motivated and engaged when things get tough?
That's a challenge with any complex subject. My advice is to set realistic goals. Break down your learning journey into smaller milestones and celebrate your achievements along the way. Connect with the wider quantum computing community. Join online forums, attend webinars, follow interesting people on social media. Sharing your experiences with others who are on the same journey can be incredibly motivating. And remember to connect the theory with practice. Use those hands-on platforms to experiment and see the concepts you're learning come to life.
It's like seeing the magic happen before your eyes.
Exactly. That can really reignite your enthusiasm.
You mentioned connecting with other learners a few times. Why is that so important, especially for beginners?
Learning in isolation can be tough. Online forums and study groups, places like the Qiskit community, IBM Quantum Slack channels, even subreddits like Our Quantum Computing, they offer fantastic support networks. You can share your progress, ask questions, get help when you get stuck, and learn from others who are going through the same thing.
It's like having a global study buddy.
Precisely. You can also look for local meetup groups or online events that focus on quantum computing. These can be great ways to network with people in your area or learn from experts from around the world.
And what about mentorship? Is that something beginners should consider?
Absolutely. Having a mentor, someone with experience in the field, can be invaluable. They can offer guidance, support, and help you navigate the learning process more effectively. You can find mentors through university programs, research labs, or even online communities.
So actively seek out those opportunities to connect with people who have more experience. They can open doors and offer a different perspective. Now, one thing we try to do on this deep dive is to break down complex ideas and make them more accessible. Do you have any tips for beginners on how to translate those sometimes abstract quantum concepts into everyday language?
One of the most effective techniques is to use analogies and metaphors. We've used a few already, like comparing superposition to a spinning coin or entanglement to a pair of gloves. When you encounter a new concept, try to come up with your own analogy that helps you understand it. For example, you could think of quantum gates not as simple on-off switches, but as more like dimmer switches that can adjust the brightness of a qubit superposition.
So look for those parallels to real-world things. It makes it so much easier to grasp.
Another great way to solidify your understanding is to try to explain it to someone else. Pick a concept, summarize it in your own words, draw a diagram, and then explain it to a friend or family member. You'll be surprised how much this process helps you to clarify your own thinking.
It's like teaching is the best way to learn.
Exactly. And it also helps you to communicate these complex ideas to others who might not have a scientific background.
Which is incredibly important if we want more people to get excited about this field. Now, how can someone who's just starting out, who's maybe in those first few weeks of learning, how can they see the relevance of quantum computing in their everyday lives before they're, building quantum computers themselves?
It's a good question. Even at a basic level, the principles of quantum computing can change how you think about problems. The idea of superposition, considering multiple possibilities at once, can be applied to all sorts of challenges, not just scientific ones. And understanding the potential of quantum computing, even just having a basic grasp of it, can foster a more innovative mindset, a willingness to think outside the box.
So it's not just about the technology itself. It's about a new way of thinking.
Exactly. And as you learn more, actively seek out real-world examples of how quantum computing is being used today. Look at those case studies in drug discovery, logistics, artificial intelligence. Seeing how it's being applied right now, that can really bring it home and make it feel less abstract.
It makes it feel more real, more tangible, and it highlights why it's worth investing the time to learn about it.
Right. Now, looking ahead, what advice would you give to beginners who want to make learning about quantum computing a lifelong journey?
Like, how do we stay ahead of the curve in a field that's evolving so rapidly?
The most important thing is to embrace the fact that this is a journey. It's a continuous process of learning and discovery. Make a commitment to stay up to date with the latest research, follow the leading researchers and institutions, and attend online events. As you become more comfortable with the basics, start exploring more advanced topics that pique your interest.
So never stop learning.
Yeah.
Never stop exploring.
Precisely. And think about your long-term goals. How might quantum computing fit into your future career aspirations or personal interests? Having those long-term objectives in mind can help to guide and sustain your enthusiasm for learning.
So whether you dream of contributing to cutting-edge quantum research or simply applying these ideas to other areas of your life, the key is to keep that fire of curiosity burning.
Couldn't have said it better myself.
This has been a truly fascinating deep dive into the world of quantum computing. Thank you so much for sharing your expertise and for making this complex subject so approachable.
It's been my pleasure. To recap, quantum computing might seem intimidating at first, but it's becoming more and more accessible to everyone. There's a wealth of free resources out there and amazing communities to support you.
It all starts with taking that first step.
Exactly. Build that strong understanding of the fundamental concepts like superposition and entanglement, and then get hands-on experience with platforms like the IBM Quantum Experience and the Microsoft Quantum Development Kit. Remember, break down your learning into smaller steps, connect with the community, and never be afraid to ask questions.
Every expert was once a beginner.
And maybe the most profound takeaway here is this. Understanding quantum computing isn't just about mastering a new technology. It's about unlocking new ways of thinking and problem solving that can be applied in so many areas of our lives.
It's about expanding our minds and seeing the world in a new light.
Exactly. So as you embark on this quantum journey, remember the vast potential this field holds. Even a basic understanding of these ideas can be incredibly valuable in shaping our future.
So keep exploring the amazing world around us, one deep dive at a time.
And never stop asking questions.
See you next time.
Goodbye.
Bye.